Welcome back to Discrete Mathematics. Last time we looked at homogeneous recurrence relations. Today we're going to solve non-homogeneous recurrence relations. So previously we saw a relation like an minus 1 is equal to k, and we had a nice fancy formula for this. So you've actually already seen a non-homogeneous recurrence relation. Why is it non-homogeneous? Because our difference between terms is equal to something other than 0. So that makes it non-homogeneous. So before I said, hey, look, if you have this an minus 1 and it has some sort of constant in front of it, the solution doesn't work. And that is true. So what happens when we have a situation like an minus 2an minus 1 is equal to 3 to the n? If this were just 0, well, we'd know what to do, but it's not. It's 3 to the n. So let's take a look at what we can do here. Well, before we begin, we should probably take a look at the general strategy. So what we want here is when we have this long recurrence relation, it's just formulas for saying coefficients plus terms to however many terms it goes to is equal to some function of n. So for instance, 3 to the n is a function of n. Then what we do is we split it up into two parts. We get our homogeneous solution, and then we add the particular solution. So think of this sort of like a vector solution. Say you have a point that you're going to over here. So this is the general solution, but then you want a particular solution, so you shift it upwards, and then you end up with the full solution. So kind of like an x and a y makes an xy vector, or something like that. So kind of what we're doing with homogeneous and non-homogeneous solutions, we add the particular to the homogeneous solution. So this is why it's very important to know how to do the homogeneous recurrence relation, because it's expected in every problem of non-homogeneous recurrence relations. So what we do for the particular is we guess the form of the solution, and then we're going to substitute the form in to get the correct results. This might seem unintuitive and challenging at first, like how do we know what to guess? But I have a nice little chart for you. So if the function is just a constant, our guess for the particular is just going to be some constant a, and we're just going to find that constant. If it's an n, it's going to be a constant times n plus a constant. If it's n squared, it'll be a constant times n squared plus another one times n plus another constant. So these, you can kind of see a pattern here. If it's r to the n, then the solution to the particular is going to be some constant times r to the n. So again, we're just sort of solving for coefficients once more. There are other types, for instance, if there's sine or cosine, but those won't be covered, so we won't look at those. Okay, so possible forms might seem a little bit confusing because you don't know what we're doing yet, so here we go. Let's do one. an plus 1 minus 2an is equal to 2 to the n. So what do? We say an is equal to the solution to the homogeneous plus the particular solution. So let's find an of h first. Okay, so we have an plus 1 minus 2an is equal to 0. So that's what we're solving here. So the characteristic polynomial is going to be r minus 2 is equal to 0. So we have a root at 2, which means that an h is going to be some constant alpha times 2 to the n. Okay, this is where we stop for now. So this might seem a little unintuitive, but because the whole recurrence relation is the homogeneous plus the particular, we can't solve constants yet, so we cannot solve this alpha yet. So now what we do is we solve for the particular, which we'll call a and p. So this is the case where an plus 1 minus 2an is equal to 2 to the n. Okay, so our form here is some constant to the n, which means that our guess is going to be a times 2 to the n. So we're just going to substitute a 2 to the n into each of our positions here. So because we have a n plus 1, we are going to substitute in a times 2 to the n plus 1. Now, here's something you might be thinking, and I've waited until now to show you, but we have a solution that's 2 to the n here, and we have a solution that's 2 to the n here, and in our homogeneous solution, we also have a 2 to the n. And what happens if we have similar roots? Well, we have to multiply by n for the second case. Because just like before, if our guess is just 2 to the n, and it just happens to be some constant times 2 to the n, then we just get alpha plus the constant times 2 to the n as a solution, which we know can't be right. So we have to multiply our guess by n for the same reasons we had to do with the homogeneous solution. So that means that this a down here is also going to be multiplied by n plus 1. Why n plus 1? Because we're substituting it in the position of a n plus 1. So let's do the substitution for minus 2a to the n in white. So now we'll subtract 2 because we keep the constant, and now we substitute in a times 2 to the n times n. And this is just going to equal, we'll do this in green, this is just going to equal 2 to the n. So now we want to solve and simplify. So we have a times n plus 1 times 2 to the n plus 1 minus, well, we can put this 2 times 2 to the n together, so this will be 2 to the n plus 1 times a n is equal to 2 to the n. So let's divide everything by 2 to the n, so that way we can reduce this right side to 1. Okay, so that means that 2a n plus 1 minus 2an is equal to 1. And because we divide 2 to the n plus 1 divided by 2 to the n, that just leaves 2. Okay, so now let's expand. 2an plus 2 times a minus 2an is equal to 1. So this means that 2a is equal to 1. So a is equal to 1/2. So what we have here is that our particular solution is going to be 1/2 times 2 to the n times n. So again, we could simplify this and say this is just n times 2 to the n minus 1, because 2 to the n divided by 2 is just 2 to the n minus 1. Okay, so we have a particular solution here, which is n times 2 to the n minus 1, and we have our homogeneous solution alpha times 2 to the n. So our total solution an, of course we know, is anh plus anp. So this is going to be alpha times 2 to the n plus n times 2 to the n minus 1. So now we can finally solve for coefficients. Well, what do we know? We know that a0 is equal to 1. Okay, so let's go down here, and we'll say that a0 is equal to 1, which is going to be alpha plus 0. So alpha is equal to 1, which means that a of n is going to be 2 to the n plus n times 2 to the n minus 1, which we can just factor out 2 to the n minus 1 times 2 plus n as our final solution. And this will be for n greater or equal to 0. So we could test some numbers out if we want. What do we know here? So let's get a list of numbers going. So a1 minus 2a0 has to equal 2 to the 0 is 1. So that means that a1 minus 2 is equal to 1. So a1 has to be 3. Okay, so then that means that a2 minus 6 has to be equal to 2. So a2 has to be equal to 8. Again, I'm just plugging some numbers into the recurrence relation. Okay, so a1 is 3, a2 is 8. So let's just verify that a2 works. So we should have that a2 is equal to 8. So a2 is equal to 2 to the 1 times 2 plus 2. So this is going to be 2 times 4, which, yes, is equal to 8. So it works. Okay, let's do another practice problem, just a little bit bigger. So this is where you really have to know your solutions to homogeneous recurrence relations and be able to do them pretty quick. Because if I said, hey, you have 5 minutes to do this question, could you do the whole thing in 5 minutes? Well, you're going to have to be able to do that. So practice is very good. So an is equal to the homogeneous plus the particular. So let's do an of h. So we have an plus 2 plus 3an plus 1 plus 2an is equal to 0. So this is going to be r squared plus 3r plus 2 is equal to 0. And this is going to be r plus 2 times r plus 1 is equal to 0. So our homogeneous equation is going to be of the form alpha times negative 2 to the n plus beta times negative 1 to the n, because our roots are negative 2 and negative 1. Okay, now it is time to do our particular solution. So this is the case where an plus 2 plus 3an plus 1 plus 2an is equal to 3 to the n. So we should guess the form. Well, the form is still going to be a times 3 to the n, because it's some constant times 3 to the n. We don't need to multiply by n because our other solutions have been negative 2 and negative 1. So that's good. Okay, so let's see what we can do here. So we're going to substitute a 3 to the n into each of these positions. So an plus 2 will become a times 3 to the n plus 2. This 3an plus 1 is going to become plus 3 times a times 3 to the n plus 1. And then this 2an is going to become 2 times a times 3 to the n. And this whole thing is going to equal 3 to the n. So let's just divide everything by 3 to the n. So then what we're going to get is 3 squared times a. Let's just make that 9. Since 3 to the n plus 2 over 3 to the n is just 3 squared, which is 9. 3 to the n is going to be 3 times 3, so it's going to be 9a. And 2a 3 to the n divided by 3 to the n is just 2a. And that's going to equal 1. So 20a is going to equal 1, which means that our a is going to be equal to 1 over 20. So this means that our guess is going to have the solution 1 over 20 times 3 to the n. Okay, so what this means is now we can solve for the whole relation. So an of h plus an of p, and an of h is alpha times negative 2 to the n plus beta times negative 1 to the n. Remember, we figured that out earlier. And then we're going to add 1/20th times 3 to the n. Okay, so Now we can solve for some coefficients. So we want to solve for a0 and a1. a0 was 0 and a1 was 1. So 0 is going to be alpha plus beta plus, okay, 3 to the 0 is 1 times 120, so that's 1/20th. 1 is going to be negative 2 alpha minus beta, and here we have 3 to the 1 times 1/20, so this will be 3/20ths. Okay, so let's take a look at this solution of equations, or system of equations. So this means that negative 1/20th is going to be equal to alpha plus beta, and 17/20ths is going to be negative 2 alpha minus beta. So we can just add these two together to eliminate the betas. So we're going to get 16/20ths is equal to negative alpha. So we can say that alpha is going to be equal to 4/5. And okay, so we got our alpha. We also know that 4/5 plus beta is equal to negative 1/20th, or negative 1/20. So let's subtract 4/5 from that. So that means that beta is going to be negative 1/20 minus 4/5. So this should be, did I go wrong here? Hold on a second. We add, that's negative alpha, so alpha is equal to negative 4/5. That's where I went wrong. So negative 4/5, so we have to add 4/5, which means that beta is going to be 15/20, which is the same thing as saying that beta is equal to 3/4. So now we have our final solution of an is going to equal negative 4/5 times negative 2 to the n. Sorry, this should be negative 2 to the n plus 3/4 times negative 1 to the n plus 120 times 3 to the n. So that's going to be our total solution for n greater or equal to 0. So we could check some terms, but it's a lot of work. So instead, you can verify it yourself. But this is how you solve non-homogeneous recurrence relations. So now that you know how to solve them, let's do a word problem where we take a word problem and just turn it into a recurrence relation. Because this is another interesting binary digit question. Well, it's quaternary sequence. So, determine the number of n-digit quaternary sequences in which there is never a 3 anywhere to the right of a 0. So remember how we did this before? We said, okay, we're going to let an equal all the sequences where it ends with a 0, plus all the sequences where it ends with a 1, plus all the sequences ends with a 2, and all the sequences ending with a 3. Okay, so we'll draw a nice little diagram, we'll do some positions, and this is going to be the nth position. So here we have the n-1 position, n-2, n-3, and of course this is 1, 2, and 3. So if the last one is a 0, what are our restrictions? Well, there are no restrictions. So the rest of these can be done in a n-1 ways, since the n-1 can be ordered however they want. What if the last one's a 1? Okay, well then there are no other restrictions, so the rest can be ordered in a n-1 ways. If the last one is a 2, we have the same situation, no more restrictions. But if the last one's a 3, we can't have a 0 in any of these positions. So that's not okay, that's not okay, that's not okay. We can never have a 0 in any of these. So what does that mean? Well, that means for position 1, it can either be a 1, it can be a 2, or it can be a 3. So for position 2, it can be a 1, a 2, or a 3. For position 3, it can be a 1 or 2 or a 3. And for all of these positions, it can only be either a 1 or 2 or a 3. So that means there's 3 different numbers for number 1, 3 for number 2, 3 for number 3, so on. So what is that? Well, that is actually plus 3 to the n minus 1. So this recurrence relation is actually an is equal to 3 times an minus 1 plus 3 to the n minus 1. So this is a non-homogeneous recurrence relation. And you could solve it if you wanted to, because we just take an minus 3an minus 1 is equal to 3 to the n minus 1 for all n greater or equal to 1. And what are the initial conditions for this? Well, for a0, we only need a0 as an initial condition. How many strings of length 0 are there? There's 1. So how many strings of length 1 are there going to be? Well, it can be 0, 1, 2, or 3. So there should be 4. Let's check to see if it works. Okay, so a1 minus 3a0 is going to be 3 to the 0. So a1 minus 3 has to be equal to 1. So that means that a1 is equal to 4. So both of our equations, or our one equation, gives us the intuitive result. So we can assume that it's going to hold for the rest. But if you're paranoid, feel free to check more. That was non-homogeneous recurrence relations. If you'd like some more practice, you can go to trevtutor.com and you can check out midterm number 2 in the Discrete Math 2 section. And that has some more questions related to recurrence relations and generating functions. In fact, after the next video, you will be able to completely solve it. So if you have any questions, feel free to leave them in the comments below, or you can check out the website. There's more stuff there. And we also have a subreddit at reddit.com/r/trevtutor where you can post questions and I will answer there. Everything anyone has ever posted will also be there, so it's a pretty good resource, and it can be pretty much on anything in high school / very low-level undergraduate mathematics, so I will be there. Anyways, if you enjoyed it, share it to some friends, because if this helps you, this will help them. See you guys next time.